hopefully the connection would be stable enough, because in my guest house last night I could still connect, but the connection was not stable. So apologies if things break down at some point, but let's start. So this folder that you can see is already there on the shared cloud folder that I have for you guys. So basically this Gyan CFD simulation files. So I have saved 3 subfolders over here. We are first going to start with this ICEM. Now, recall what we had briefly discussed yesterday. We first built the geometries from the CT scans, right? And some of you can come on this side, because you might want to see my face. So first we start from the CT scans, and the CT scans are brought in DICOM format into a software which can segment the scans, as in pick out the correct radio density to figure out the airspace. And as I mentioned, we can do it with Slicer 3D, which is open source, which you can get here. The one that we have been using has been Mimics, which the license is kind of expensive. They might still have it here, especially if you guys have collaborations with medical schools. They pay for that because it is quite precise in the sense of how the segmentation happens. We are not going to go into the segmentation part here today. The geometries have been built and has been exported to a CAD software. For the CAD software, we are using ANSYS ICEM. You can use something else. So from Mimics, you generate the STL file, which is the geometrical structure, and you bring that STL file into a CAD software. You can use SolidWorks as well, or any other meshing tool. But along with just meshing on the CAD software, we also do the region separation. So as you saw in the work that we have been doing, I think in the second on the second day, I showed a geometry with all the sinus cavities marked out. So you can do that on ICEM in sim, or based on the question, you figure out what target sites you have to track in terms of particle deposition. So the geometry that I'm going to show today just has the nasopharynx marked out as a separate region, and the rest should be intact, the anterior airway. After the nasopharynx, there is a nasopharyngeal outlet as well. So let me first go into this folder ICEM, and I'm going to open. I have all these files saved and the mesh has been built, so I'm not going to redo everything, but basically give you a flavor of what needs to be done. So if I would encourage that you save all the folders that I have shared, and in the afternoon session you can go into the CAD lab and use these files. So I'll first open the nasal geometry, the nasal cavity geometry, which does not have the mesh. And the first thing that we are going to do today is develop the mesh file. Anyone here has used ANSYS ICEM? Okay, so this is the geometry. You can make it nicer by doing this. So on the left panel, you have the different parts that I have marked out already. So over here, as I told you, we have the nasopharynx, which is in gray. All the rest I have colored. I've given the same color, but you can right click on the parts and choose a different color. So for example, for the left airway, if I change the color to something else, this is the left airway, and this is how we do it. We distinguish between the left and the right airway, because as I have told you guys that the two sides of our nose are asymmetric. So the trends could be different on the two sides of the nose for the same person, and they are always different. Anyways, so now idea is we have to first develop the mesh before we can run the simulations. To do that, we go to this mesh option at the top, and we need to first think about what kind of mesh we are going to build. The mesh that we use, and we have published a lot on this meshing standards. We first develop the tetrahedral mesh with a certain level of grid refinement. And once the tetrahedral mesh has been built, you can use it for simulations, but there is this caveat that eventually for the biomedical applications in this space, you are trying to get regional deposition patterns, be it for infection transmission or for drug delivery. So the mesh has to be resolved, ideally, near the regions where you are tracking that particle deposit. In other words, you are tracking the particle deposits along the walls. So next to the wall, the mesh has to be finely refined beyond what is there in the best tetrahedral mesh. To do that, we will do a second layer of grid resolution where we develop prismatic cells along the walls. But that is the second phase of meshing. Let's first try to get the tetrahedral mesh built. So we go to mesh, we go to this first option under there, and this step, if you end up using SEM, it would be a trial and error thing, because as you decide the scale factor, the maximum element size, the total number of mesh elements of course would change. Now the gold standard, or I would not say the gold standard, but things that we have done mesh grid refinement studies on showed us that for a geometry like this, in the sense that a geometry that is ending at the base of the nasopharynx, and this bottom red panel, is red region, is just that tubular outlet which we keep to make sure that the flow is still well developed and we don't have any end layer effect at the nasopharynx. So for a geometry which is basically limited at the nasopharyngeal base, we saw that 4 million tetrahedral mesh elements is sufficient. So we have to figure out the scale factors and the maximum element size and the minimum element sizes accordingly. Now, if you have a model that is further that includes the further downstream tracks, so for example the 3D printed model that I had brought, you of course need more elements. So for example, the one that some of the results that I showed during the research talk, where we had the full airway till the base of the trachea, I had around 13 million elements. No, 10 million elements in the tetrahedral mesh, and then 13 million while after I built the prism cells at the walls. So 10 million is the rough number for the tetrahedral mesh if we include the rest of the upper respiratory tract. If you go further downwind into the bronchial pathways, of course you need to be very careful, because you have thinner channels into the bronchial pathways, and if you are indeed tracking delivery of particles in those cavities, in those thinner cavities, generation 2, generation 3, generation 4, there should be enough elements in those cavities as well. So that is something that my students face difficulties with. They keep, say, a certain number, certain million cells in the overall mesh, but the mesh resolution is not fine enough in those finer channels. So in that case, either you do some regional mesh refinement, or you just increase the total number of elements in the mesh. Now, if you look at your printouts, I have already included the kind of scale factors and the maximum element size that we are using here. So for the scale factor, I have used 0.9, and for the maximum element size, I have used 1. Now, a CAD software is essentially, it is a dimensionless world. So what do I mean by 1? Typically, the scale would correspond to a millimeter, right? But then don't assume that every element here would be 1 millimeter, because that is not tenable. That's why whatever settings you introduce here, you need to still keep track of how many total number of elements are being generated, what is the overall volume, that would give you the mean size of each element. And if you, based on the kind of venue journal that you go to, you might have to justify why you chose your mesh element size the way you have. And in fact, many times they would also ask for a sensitivity study. So let's go down. So let me enable the minimum size, and the minimum size that I have is 0.3. So once this is there, click apply, and the global mesh size has been defined. Okay, and then go to the next tab under mesh. So here we are setting up the parameters for the prism mesh. We are not building the prism mesh yet, but you can still set it up right away. So again, these numbers are there on your printout, and I think many of these are already saved in this file that I have opened. Now, couple of things to note here. You will see on the very second column that I have enabled some regions to have the prism mesh, but not the other ones. But if you read the names, curves actually contain the curves that are outlining each of these regions in the geometry. We don't need mesh refinement along the curves. We need mesh refinement along the left airway, especially because some clinical conditions like uh, allergic rhinitis, you might not know about the name, but that's a very common clinical condition, and there the inflammation happens along the outer parts of the nose. So we do need to, is the audio fine? Yeah. So we do need to include the prismatic refinement there as well. Left nostril is the plane through which the either the fluid or the particles are going in. We don't need refinement there because it is the inlet. So the left nostril does not have the refinement. Nasopharynx does, of course, for obvious reasons. Outlet doesn't, because there also the entire constituent is leaving the airspace. We don't need the refinement there. Right airway we do for same reason, and right nostril we don't. Tube, which is that extension that I have added at the base of the nasopharynx, I have enabled it there because what if the particles are depositing there? So we have it there. So let's press apply and then dismiss. Now we go to the last tab. Yeah, this is what I was worried about. It says network connection is unstable. So let's continue as long as we can. So let's go to this last tab. Now we choose, the default is tetra mixed mesh. So we choose that. The meshing method is robust octree. If you write journal articles, research papers using these tools, you need to mention these methods because they would like to see what you have used. And you don't need to do anything else here, just press compute. So now, based on how big your mesh is, it takes some time to get the mesh built. This one probably shouldn't take too long, but let's see. Sometimes for the 10 million, 15 million meshes, it can take, at most it would take 10-15 minutes, not more than that, but this should be quicker than that. No, this is not a solid region. This is just, so basically there is a cavity inside. This is not solid. This is just the shell. Yeah, 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 yeah. Inside is hollow. So you are building the mesh. So that is a very good question in the sense that some students do have their confusions with this. So for example, here it's a shell, the STL is a shell file. So basically, if you have something over here, if you look at the cross section, it is hollow. It is not solid, right? But if you are trying to use the same geometry for 3D printing, you need to make sure that the hollow space remains. But if you just print this, it would become a solid model if you print it. So then we have to figure out a region or basically a storage container which would contain that cavity. And that's what I did. If you remember the 3D print that I shared with you guys, I built an external structure like this. And then we meshed just this part so that the 3D printer would know, 3D printer would know what part would be solid and what part would be hollow. Okay? And we are building the elements, of course, in the hollow region because that's where you are modeling the fluid flow through, right? Funny anecdote, there was a student at SDSU, of course I will not name the name, but after working for 6 months with me, uh, building a lot of mesh files, suddenly came to my office. That, sir, I don't think this would work. I was like, why? Because I see the meshed model. It looks like the mesh model. Once I build the model, you'll see that. Let me use a different. You'll see that, of course, it is built of number of small elements, right? So her point was, this looks like a solid layer of bricks. How will the flow go through? So then and there, I basically pushed the student out of my group. So if after 6 months, you can ask that question after a day or two, at what is going on. But to ask that question after 6 months, that means that there is a very fundamental lack in basic scientific understanding. But that's a funny story. I'm not expecting anything like that from you guys. But yes, so we developed this mesh in the cavity, discretize it into the special elements, what CFD does, because there are some students in this, not many of you, but some who have not used CFD before. The reason why we do meshing, can anyone answer why we mesh? Why don't we simulate through the cavity?
Basically, we are solving the algorithm in a discretized form. So once we have the discretized form, it means that for each element that is solved. So if we are just a large element, we do not mesh it. And that means that the moment we convert the algebraic equation into the communication into the algebraic forms, that is more accurate as soon as we have the small elements.
Yeah. Assuming that you are explaining it to your maid servant, what would be your answer then? Or maybe someone in your family who has no background in science. So all the Navier-Stokes equation, the solutions are easily tractable in known geometrical shapes, right? But these are complex geometries, and solving the Navier-Stokes equation is almost impossible in such complex geometries. So we are trying to develop some regular geometries, very tiny elements, regular geometries where we can solve the Navier-Stokes. Yes, it's a numerical solution. It is using all the techniques that we have developed. But at the end of the day, we are solving the governing equation in tiny elements with a known geometrical shape. And then we are getting the global mean of that. Right? That's the idea. So not for the fluid mechanics people over here, but that is what we do. So if we are trying to develop the CFD simulation of this room, we break it up into these tiny elements where we can solve the Navier-Stokes, and then we get the overall average solution throughout. Okay, so I think the mesh has been, no, it is still going on. Yes.
What is the benefit of dividing into three or four regions?
Yeah, so that would depend on the question that you are trying to answer. So for example, if you are trying to figure out what is the, so let's assume that you are trying to track drug delivery in this, in a constrained region like this, then you have to develop a separate region on that. So you have to get the geometry into ISM, draw out a curve, and there is a way to do region partition. And you develop that particular region, name it to show up over here, and then that would show up on your fluent simulation as well. And you can directly get the deposition amount for that region. So for example, when I was doing some more clinical studies where we were trying to figure out drug delivery for sinus inflammation. There the target site is actually here, because if you think about the different sinus cavities, they are draining their fluids right over there. But then we have to develop a region right over here. We are not concerned about that clinical condition, at least for this geometry right now. What we are concerned about is, as we'll show today, that the simulations that we are going to run would be both for infection mechanics and for drug delivery. And we are looking at treating conditions that primarily affect endocrines, which covers a lot of viruses. That's why I mentioned the endocrines is not done. If you don't need the drug delivery or the pathogen transmission of the endocrines, you don't really need to get this as a separate part. Maybe you need something else, and then you keep that. Of course, if you have extra regions, it doesn't matter. You have those, you have extra data in your simulation. Does it make sense? Okay, so the mesh has been built. So yeah, it would be easier to handle if you have a local computer, but over here, let me just use this. See, the total elements is 4052013, 4 million. So that was the gold standard that I was trying to hit. And that's how I got those meshing parameters, because initially I probably got something less than 4 million or sometimes more than 4 million. More is great for simulation, but of course, if you are trying to numerically solve Navier-Stokes in as many number of elements, the simulation takes longer, right? So, for example, this simulation, if I run it, it probably takes a day at most. But the full airway simulation with the 13 million elements, that took me. The computer was not doing as well, but it took me around 11 days. So it's a function of that. So it's the time cost prohibitiveness that you need to think about. But 4 million is fine for this one. So the next thing that, and this is the so if you look at your printouts, so we are done with this particular one, and this is the second screenshot is this one. This is exactly at this step. Yeah, the second and third ones is where we are right now. Okay, now let's try to develop the prism mesh, because the tetrahedral mesh has been built. So for that, we go back to over here, and we change it to, so basically we go to this one. So this is for prism mesh, and you are building the prism mesh on the existing mesh, and that option would show up, because you are not doing anything with the tetrahedral mesh. You actually need it, but you are developing the prism mesh on top of it. Now, one thing that I do as a good practice, because the tetrahedral mesh might be useful sometimes as well. So I would suggest that before you develop the prism mesh, you save this. You save the tetrahedral mesh that you have already built. And before you save it, it might make sense to check the quality of the mesh. And you can do that by going to Edit Mesh over here. And this fourth tab, Display Mesh Quality.
Can you suggest any book for like you can get a clear idea of how to do the meshing, like means whether to use different mesh or with other meshes or
RF's book could still be useful in terms of the basic understanding.
are you studying full form?
Hassan Aref and S. Balachandar. Because basically that is the book I like for all this. Yes, it is. It is just noted down Hassan Aref. He is my academic grandfather, by the way. Hassan Aref and S. Balachandar. Search for computational fluid dynamics. Okay, so if I go to this fourth tab under Edit Mesh, display mesh quality and press apply, you'll see that basically they classify the meshed elements in terms of their quality. How do I define as quality? It is how smooth the geometry transitions are from one mesh to another. Now, this is fine. The thing that we track is in the worst quality bin, which is the bottommost menu, if the percentage is close to 0%, which it is, but if it is not, there is a way to smooth the mesh as well. So which you can do that by going to this fifth tab, and there is a smoothing iteration. You can do it some number of times. If you do it too many number of times, then you might lose some of the anatomical topological accuracy. So don't do that too many times, but you can do that as well. This third tab checks the mesh for any kind of errors. So these are the errors that might show up. You can read them, but the most common error that I have found happening is there is a hole in the mesh. Or when we have done the segmentation and we have built the geometry, there are some hanging elements. So there's some hanging part somewhere. The reason why this happens is when you are doing the segmentation, so let's assume that this is one of the slices because we are taking around 200 to 300 slices, right? So let's assume that in this particular slice, this was the airspace. In the subsequent slice, the airspace changed to something like this. Now, this element over here might not have, so if in second slice we picked such that that element does not have any continuation into this picture, a smooth continuation, this keeps on residing in the solid geometry, and it keeps on residing there in this 3D reconstruction as well, and it becomes a hanging element, and you don't want that. So you need to make sure that that is not there. So that is one source of error. The other source of error is when you do this regional partition, you'll see that sometimes some surface artifacts pop up which is inside the cavity, and you need to delete them. And some of these are software issues, and which you basically learn with using the software again and again. And I've had a hard time when I first started using it back in 2016. But that is something that comes
So
with
does it
practice.
show any written warning or you have to?
Yeah, sometimes you have to figure it out. You have to zoom in and figure out where the problematic elements are, and you can create a subset of those problematic elements and go back into that particular stage where you actually used that particular region and make sure that the pixel selection is smooth enough. Now, if you guys collaborate with me, thankfully that part we have dealt with already because these geometries are already built and we have around 100 such geometries already built, but that is a painstaking process getting that built. And in fact, like a couple of years back, a group contacted me to build geometries for bat airways, and the scan quality was so bad, the segmentation was not that straightforward, and there were so many hanging elements in there. Okay, so I'm not going to do the smoothing. Let me show you if I do the check of the mesh. So I press apply under the check mesh. So no problems were found for duplicate elements. And it is carrying out the other checks.
How we can check discrimination of the discrimination.
Uh, do you see that option here under the check mesh on the left panel? Could you repeat again? What error are you talking about?
Discrimination.
The skewness. The skewness. The skewness. The skewness is something that we can. So as you will see when I set up the prism mesh, there was a skewness factor as well, which has been tested to see if it works or not. So I don't think the skewness factor is there as an error option here, but that is something that we set up when we build the mesh. Okay, hopefully we don't get disconnected. Yes.
How many numbers of prism lens will be?
Yeah, so that's a good question. So that is also coming from our mesh sensitivity studies. You can pick 3 layers, 4 layers, and we have run studies where we have picked multiple number of layers to check if there is any difference in the eventual position data. So I think for this one I used how many? I believe 3 layers. Yeah, so I've used 3 layers with the overall height, the total height being 0.1 mm. But you can choose 4 layers as well. But based on the journal that you are going to, you have to justify what you are choosing, and you might have to run a mesh sensitivity study. Sometimes you can cite published works in this domain that this is what has been done and has been tested to work. Okay, so it's back. It's still going on.
So if we have this already tetrahedral mesh,
Yeah.
for that we are using the prism layer.
Yes.
Is it possible? Like, it may happen that already that it is a well-defined mesh, but it may get unstructured after injecting the prism layer, or that is not the
It
case.
can happen. So we will do the mesh quality check even after building the prism mesh as well. Okay, so once the mesh quality check is done, you'll get this diagnostics message, which you'll say yes, delete the unconnected vertices, because otherwise there will be an error in the mesh. So yes, and now the mesh is done. So let's save this. So save project as. So I'm going to call it Jan 22 nasal cavity geometry, but as a good practice, what I do is just change the name of the last part of the extension. So this is a tetrahedral mesh, so tet mesh. And sometimes, as you see on the existing file over here, which you have access to, I also mention the number of elements that were there, especially when you are working, developing a number of mesh files. But let's keep it like this. Okay, so the tetrahedral mesh has been saved. The next part is building the prism mesh. So for that we go to this. So the prism mesh setup has already been built. That table that showed up, and if you go back there, just to review, uh, actually not everything has been set up yet. So let's set those up. So the maximum size is not there. So let's do that. So you can directly pick it from the by clicking on the item name, and the maximum size is 1. It would be activated on all the parts, but since you have already activated some regions where it needs a prism mesh, the other ones won't matter. Now for the height ratio, we are going to use 1. The number of layers is 3. total height has to be changed as well. So let's change it to 0.1. It's the height that spans those three layers. So that I'm picking as 0 0.1, sorry. And what else? We have the tetra size ratio, 1.1. Did we cover everything? So it's on the on the first printout that you have today. So 1, 0 0.1, 1, 3, and 1.1. Okay, so apply, dismiss, and then go to the last tab under mesh, and then pick the prism mesh and then compute. So folks who have used ANSYS before, did you guys so the geometries were engineering geometries or any irregular geometry like this?
These are regular.
Regular. But you did it as well, right? So what was your geometry like?
So links. Currently working on fluid effect interaction modeling of dynamic links.
Okay, okay. And did anyone here do ANSYS modeling? So these meshing parameters, they actually come down from different academic lineages, the academic families who started working on in this domain. So I'm not going to claim that everything was done by me. So many of the standards that I'm showing you here now, these are things that I've learned when I was a postdoc.
Like for example, in this we have a shot. I have seen like one where they exclude the internal volume of the shot and only like
Okay.
here we are not doing it that way.
What tool do they use for the meshing?
Formation only on the
ICM.
they have just
Yeah. Is it a 3D mesh or a 2D mesh? 3D mesh. So the prism mesh typically takes longer because now the mesh is getting more refined in certain regions.
Sir, why we are not using quadrilateral?
Why we are not using what? Quadrilaterals?
Why
Yeah,
we are using this?
like your question is why we are using tetrahedral mesh and not something else, right? There's no reason why. I mean, you can try it out with other kind of element shapes and check whether your results eventually they agree with the ones in literature.
Because that the quadrilateral is quite uniform.
Yeah, you can try other methods as well, other element shapes. And there is no physical reason why, so that's why I cannot give you the answer. But these as I'm telling you that these are the gold standards that have been seen to work in terms of validating the eventual computational results with experiments as well. So when you use something else, you have to justify that the validation would still work. And sometimes it might be, it would, like if you're thinking about publishing those results, it would depend, of course, as you know by now, who reviews your papers. If that person knows the literature inside out, then you will have to answer the questions like why you are deviating from what has been shown to work in this particular space. Okay, so as this one gets built, let me take the time to walk you through something else. So if you go back to the Gyan's CFD simulation files, I have uploaded the protocols as well over there, so you don't need to remember everything from what we are doing. I don't think I have Acrobat Reader on this particular machine, so I won't be able to open it. But this meshing protocol, it outlines step by step the things that we are doing now. So when you try this on your own in the afternoon, you don't have to recall everything that I did now. You can open up that document, it's a PDF document, and follow the steps. Okay. So this is the meshing protocol, and I have the protocol for the flow simulation. This is the alias protocol, the last one. And then for the inert particle DPM method, the protocol is there, but we are going to do it both for drug delivery and for infection transmission. And for the way the particles are inserted into the domain, they are different in the two cases. So for the drug delivery application, the particles are going to go into the airspace with in a conical shape. So there we need to figure out a point where the spray nozzle is located, and then we need to identify the coordinates of that point, set it up. We need to know what is this angle, and then the particles are going out like this. So this is for drug delivery. For the infection transmission, we are breathing in the aerosols, right? So there the particles are going in like this through the nostrils line. So although we are using Lagrangian DPM tracking for particle tracking, the way the particle insertion is set up is different for the drug delivery applications versus the airborne pathogen transmission application. Okay. Now, if I go back to this folder again, that one has all the protocols. The ISEM folder, in the afternoon, you can start from the nasal cavity geometry and test out whether you can develop this mesh, that thing that I'm doing now. But even if you cannot get to the meshing stage or the eventual output of the mesh, I've already saved the mesh file over here. So the mesh that I'm going to use is this mesh UNC071. That's the actual clinical identifier for this geometry, so you may note it down. UNC071 prism mesh is the one that we are going to use. So the mesh files would be in .msh format. So the mesh files that would be generated from this exercise would be needed in the first folder, which is the Fluent folder. There also I have already saved the simulations. So the simulation that we are going to use is this one, nasal cavity prism mesh flows out the 2021 same 30 liters per minute. There was some issue with the first one. It still worked, but there was an issue which I have mentioned in the lecture notes, but let's not get into that for this one. There was an error that I had to correct at the Fluent stage. So we are going to use this 30 liters per minute 2021 simulation. So this is the flow field. Once you have the flow field, as we saw the workflow, the flow field is going to impact the particle transport. The particle transport is going to be inert and not impact the flow around it. So once the flow field has been saved, then these subfolders over here are the particle tracking simulations for respectively for drug delivery and pathogen transmission. So if I open one of them here, so this again, this second file over here, 2021 cm 30 liters per minute, this is the flow particle salt, which has all the particle generation information based on this particular setup, where all the particles are entering through the nostrils then. So that is for pathogen transmission. For the drug delivery, it is set up with the conical injection that I showed. Now, under each of these folders, you will see that there is another DPM folder where I have saved the particle deposition data for just 10 micron particle. Of course, for a real work, you have to go through a whole range of particle sizes. But we are going to generate this 10 micron data, hopefully, and then compare that with some of the published
These
works.
10 micron particles are just treated as some points, or you, like, let's say you are putting like different size particles. How are you assigning the size?
So the size dependence only goes into the drag force calculation because it's a function of the size, right? The diameter. But otherwise, because the particle cannot impact the flow field, it is a point particle.
So you just put some points and then do random tracking.
Yeah, 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 yeah. So you need to know the coordinates from where the particles are starting out from. Now, in terms of the pathogen transmission one, those coordinates are the centroids of the surface elements in the mesh. On the other hand, for the conical injection, because the spray is supposed to be inserted inside the airspace, you have to actually figure out what are the coordinates from where the particles are going to be ejecting out. And they are point particles, yeah. Now, if you, for example, if you are looking at red blood cells, they are not spherical, right? Uh, so you can use user defined functions to tell Fluent if the drag force formulation needs to be changed. There is a shape factor as well that you can control for those applications, but we don't need to worry about them here because we are assuming the particles to be spherical, and that is what the default is. It would assume that whatever that the diameter is, it is that the 10 micron is the diameter. It is a spherical particle, and it would calculate the drag accordingly. Okay, so this is the layout of the folders here. So even if you guys don't manage to do much on your own in the afternoon session, you will have access to all these files. And if you ever want to get started on this area, you can just run through these files. Yes.
But this live expression will also mention the function shape of the
Yeah. Yeah.
how we with respect to the organism. So everything we cannot directly interpret.
If you don't do anything, it would by default assume it's a spherical shape. But then if you want to control the shape factor, you can do that using user defined functions into math in Fluent. Now you can figure out what the shape factor could be for a different shape, whatever shape we are trying to track. But then again, there is this limitation: is that shape would get fixed. It would not deform because that is not supported under the inert particle tracking. Rigid particle with just a different shape factor, basically. Okay, so the meshing is still going on. I think we should be very close to getting done. So, in terms of the protocols, I have included them. So, if you go to the lecture notes file, that PDF, that big PDF, I think I have included the protocol there for the meshing, but I probably did not include the protocol for the flow simulation, which we are going to do later on today. For that one, you just access it directly from the protocols folder under the Gyan simulation files. Okay, so it is done. Let's now see how many elements are there. So you'll see that what we had before was 405 or 4.05 million elements. Now we have 4.45 million elements thanks to the refined layers at the walls. Okay, so we typically report this number of elements in our papers, how many elements are there. Now once this is done, we again go to edit mesh and we do the same exercise. We want to see the mesh quality. So if I opt for that, and now you see that there are quite a bit of elements, although if you think about the total percentage of elements in terms of the overall number of elements, it's just 1.3%, but still 57,000 is a big number. So let's see if I can reduce that. And to do that, we go to the smooth mesh globally. You can do it locally as well if you know the problematic areas, but most of the times using the global refinement works. So you can change these values. It the default is 5 iterations and till point 2. You can change this point 2 number as you go on. So let's first try with point 2. Apply. So I clicked it twice. So it really did not change much. So let's increase this to 0.25.
Maybe I was like respect to linear dimension of this.
Yeah, it did not change much. Let's make it zero point 0.3. And you don't want to go too much because too much of smoothing can actually, as I said, disturb the anatomical realism of the geometry. It is not changing much. So from 1.293% we went to 1.2%. I would stop it here, but for things like this, my advice would be to make sure that you report this in your work. That this is what the worst elements had, how many bad elements were there. Okay, so once this is done, we go to the check mesh again. And checking the mesh is critical because sometimes we build mesh, we output the mesh, and then we import the mesh into Fluent, and then Fluent tells us that it's a bad mesh. And that's unfortunate. Then you have to again go back and do this entire exercise again. So let's do the check mesh. And at this point, sometimes you see that there are problematic elements which you can create separate sub parts which you can fix locally. You might have to go back again to the segmentation stage and make sure that that transition from one set of pixels in one slice to the next slice where the same pixels are in the same region, that transition is smooth enough. So when was medical imaging discovered? All this medical imaging data that we are using, when was it first possible to get medical images? It started with the one in the it started with Wilhelm Ronson, right? With Express. That's like early 1900s. It's probably early 1900s. Now, recently, I'm taking this time out because, and it could be part of the lecture. That's fine, but it would take a while to check the mesh. Recently, I came across this paper where this person. No, that was before that. So I was at a conference. I was at the DFD conference.
1895. He won the
1890.
first Nobel also.
Won the first Nobel. Yeah,
1801 he won. He is the first recipient for
yeah,
Nobel Prize in Physics.
yeah. So I was at the APS DFD a couple of months back, and some of you were there, right? Anyone here was at the
No,
DFD?
from Chandra's group, I guess.
Chandra's group. Okay. And at night, I finally managed to turn the television on. By the way, I'm very bad with technology. I have not been able to turn the television on in my guest house yet because it's a smart TV. So I don't know how to operate.
Maybe you have to switch on the switch, but they don't have it
I
put
switched
it
it on, but the remote is so futuristic.
The battery is gone. That is also.
No, the battery is there.
Okay.
Anyway, so I did manage to turn the television on in the hotel room, and the show that was going on was on Leonardo da Vinci, or Da Vinci, whatever you might call it. And this guy, you know him, Moteza Karib Caltech.
Most of the
So he ran some. So if you look at Leonardo da Vinci's sketches, he did a lot of sketching in different areas. Like for example, in my PhD thesis, if you access my dissertation, it is available through my website. My PhD dissertation was on vortex wake modeling, where you have a bluff object, wakes are formed. What is the most common vortex wake? The one common, with two vortices in each cycle. But as you increase the number of vortices in each period, it becomes very complex. So in my PhD, I looked at systems with four and three vortices. Uh, and Leonardo da Vinci actually drew some nice sketches where he showed these different smaller scales of in the wake structures, which is amazing because like he did not have a way to take high speed camera imaging, right? So I added that picture in my dissertation. But at that point of time, I knew, but I was not that aware that how much he has done about human physiology in terms of sketching. So when I was watching that show, I knew by then that he has done a lot of work. But Moteza Gharib is a turbulence guy, right? If I Devananda Gharib does a lot of turbulence modeling, right? Yeah. So he was focusing on the turbulent, the sketches on turbulence. But then I got interested and I came back and I purchased the notebook. That's what they sell it as. It's a big book like this thick, of all of Da Vinci sketches. And I wanted to see if he has done anything with the airway. And he of course has. So he has sketched the airway and the bronchial branching. And there is this guy, I think he's a doctor somewhere in Europe. He does some modeling, but since he is a doctor, he does not get too much into the fluid mechanics. So he did some modeling, but looking at those sketches, it is amazing. Like he did not have access to any kind of medical imaging, right? He probably just did some cadaveric sectioning and drew those images.
Yeah,
So
he had this famous picture of like large like amount of water falling in from a drain falling into a tank, and all these large eddies, small eddies.
small it is.
Yeah, there is no concept of even turbulence that time, but he just observed the whole flow process, and like today we can see scale that the turbulence is like a large from a big scale to smaller scale that so many vortices appear. But in his like he is starting with the largest eddy, then like the smallest eddies are appearing.
And
Yes.
he just observed those streams, and he does not have a snapshot in time, right? He just looked at the overall averaged visual data and drew those sketches. So if anyone here wants to write a paper which would get noticed straight away, pick up Leonardo da Vinci and pick up whichever system you are comfortable with. Figure out the corresponding sketch from his workbook. Try to develop the digital model of that. Run some analysis, run some CFD, and there is a very high impact paper for you. So I was telling my
There was
friend,
a scientist called Troy Singh. He also visited OS. This is some Rutgers University basis or something. He like once he has a few science and nature papers. He said like he does fluid mechanics and many other things also, but mostly classical physics. So he said like okay, suddenly I looked up some papers of Lord Rayleigh and Lord Kelvin and then work on it. It turns out to be still there are many interesting things which can
yeah,
be explored.
yeah. So yes, if you ever run short on ideas, this was a big fear that I had when I was at your age when I was finishing my PhD. That I'm being guided by my PhD advisor. The ideas are primarily coming from him. So what would I do when I'm on my own? Uh, but if you ever feel like that, just purchase the Leonardo da Vinci workbook. Okay, so we are, I think, close to getting done here. So delete the unconnected vertices again. So yes, and the mesh quality is fine. And I'm showing it here just as an exercise. Of course, I have already built the mesh and they are available for you. Now to generate the mesh, we go to the output mesh tab and go to the first option here. And this would let you generate the mesh in different for different package softwares. So Fluent is of course there. What else is there that might be interesting for you guys? So Star CCM Plus, is that anyone here uses Star CCM or on this campus?
Mostly
No.
as this, maybe some solid work like use. But they also use avocado.
Yeah, Abacus should be here as well, I think. No, it's not there. Anyway, so ANSYS Fluent is what we are going to use. So apply and then go to the last tab over here. Oh, I have not saved the project first, so let's save it. And I don't want to overwrite anything, so let's close it now. And so it's going to change a few things. That's bad. So let's do it this way. So save project as. Now let's call it Jan 22 Prism Mesh. Another way to get new ideas, I know all of you go to conferences now, right? So as PhD students, one big mistake that I used to make was just attend the vortex dynamics sessions, because vortex dynamics is what I used to do. Try to attend other sessions as well, because if you just stay within your own very small subfield, you don't know about what is going on in the other fields. So especially when you go up as job candidates in the academic domain, it is important that you know what is going on overall. Okay, so let's now output the mesh. So this is
After that.
okay. Output mesh and then go to this last tab. The project has been saved, so no. Now you pick the corresponding file. So this is this file. So open. Now, if you don't do anything at this stage, the mesh would be named as Fluent. We don't do that because then things get confusing. I would copy paste this BOCO file and use that as the mesh name. And done. So now if you go back to your the directory folder that you are working from, which in our case is the Gyan CFD simulation files, ISM for CAD. So you see that this file is getting built. It is going to get bigger as long as it shows up here that it is growing. You see it is growing. So that's what we do to develop the prism mesh, and the prism mesh that we are going to use or you are going to use in the afternoon. Uh, you can use this one that we have just built, but you don't have access to this, right? You will have the ones on the cloud folder. So use the one called UNC071 Prism Mesh. It's exactly the same as what we did today. Now once the mesh has been built, we will import it into the Fluent to run the flow simulation. So in the next session, we can set up the flow simulation. The other thing that we need to do, which needs some ICEM work, is figuring out where this location is for the drug delivery application. Where is the nozzle placed? And to do that, that would occupy one session. I should not do that for the sake of time. What I will do is I will open the work that I did and show you how it's done in broad stroke. I think all of you are smart enough to understand how, if you have to do it from scratch, how it should be done. So in the second session, we will do the flow simulation, and then in the hopefully in the following session, I'll show briefly how to get this one done, and then go directly into particle tracking. We'll do particle tracking, get the data, and then go and compare that with published papers. Now, what are the timelines that we have today? Let me think a little bit because today is somewhat different.
Can you assume 2 to 3 and then what is the poster session? 4 to 5.
Yeah, 4 hours.
Okay, okay.
So my target would be to
Maybe you can start like I don't know 1:30 to 2:30 and then 2:45 to 3:45, something like that, and then whoever wants to go to that your conference can go.
so what my intention would be to show the work or do as much of the work that I can show you guys and do it on my own. Because
so you
once
can just like now it is just 1 hour gone. Then maybe like we can also like extend the next session by 1 hour 10 to 15 minutes. Just
okay.
to be more nice.
I mean I would like to stop at logical time points. So basically flow simulation I'll stop it there and then do this part and then the particle tracking. And if there is time, then we can compare the data with the literature data. But if we don't have time, then keep it for the subsequent session. But what I was hoping that I think I was misjudging how long time, how much I would need to get these things done because I'm explaining certain things to you guys, so it's taking longer. So even if you don't have much time to do any work on your own, I think I'm giving you enough cues so that if you are interested, you can do it and you can get in touch with me anytime you want. So let's continue this way. In the next session, we are going to do the flow simulation.